All right. It's a pleasure to be here, and the presentation is about toward the multi-scale learning of adhesive contact forces. My name is Ali Maghami, and I've been working with Merton Stende, Michele Giavarella, and Antonio Papangelo from Politecnico di Bari, and also TU Berlin. First, we will talk about the motivation of the works, then I will describe the physics problem, and then I will present two types of learning models. I mean, the first one is the surrogate scalar model, and then the other one, a scalar model, and the other one is the full trajectory deep learning. Then we will have the results and outlooks for the future works. So in general, fast prediction of the adhesive forces, in fact, the real-time prediction of adhesive forces have many applications in control and design of surfaces. I mean, we saw applications in, manipulations and soft robotics. And in general, solving the adhesive contact problem requires a lot of computational efforts through the numerical simulations, and also some inspiration from the nature could also be made. For example, looking at the geckos and thinking that do they really solve these nonlinear equations with their tiny brains or not? I mean, so we just moved to the simple problem of Hertzian contact problem, which we had the spherical rigid indenter, which is going through the adhesive surface of viscoelastic material. And we considered a simple type of loading of three-phase with loading, dwell time, and unloading. And then the material is also considered to be viscoelastic. It's also very similar to the graph and Grisping applications. So we then started with a boundary element simulation. So for the numerical simulation, we considered the modified power law material for the viscoelastic material defined by William. And for the interface adhesion, we considered the Lennard-Jones potential. We built our simulations. Then we finally achieved something like the plot that you're seeing on the right side, which is related to the force versus time. And the goal is to have such a simulation. And we know that, to have a proper application, we need to have for a vast majority of the viscoelastic material and also geometry of the surfaces, we need to explore these parameters as the input to the boundary element simulation. So for each simulation, it might take a lot of time to achieve such a curve. So we first were interested to achieving a pool of force, which is the maximum force that you're seeing on the top, to be able to predict it. And then we went to the analytical simulation. We went back to the physical modeling that was presented by Persson and Werner, which is more related to the crack propagation in this viscoelastic material. And the solid line that you're seeing here are the result of Persson and Werner theory. And the dots that you're seeing are the pool of force that we obtained through the boundary element simulation. So we just tried and we fitted the analytical simulation and the boundary element simulation. So it's also showing that the boundary element simulation quite well. However, when we just looked at the model that we achieved, one can conclude that maybe the analytical simulation is enough. So we just have the very fast prediction of the forces. However, when we just look at the limitation and assumption in the analytical simulation, we would understand that it only works for the long dwell, large preload, and also large Tabor parameter. I mean, Tabor parameter is also a geometry and also material properties inside the, adhesion field. So we have a model that predicts very well, very quickly, but it also has some limitations. We also looked at the, exploration space with the application that might an adhesive contact property have. So we just plotted it, and this is the, the exploration space of the material. And it is also color-coded. It means that the red shows that the computational costs that we have, and also, the shaded area that you are seeing on the cubes are also showing the analytical simulation or the solution that we have in real time, while For the rest, we don't have anything. I mean, we should rely on the boundary element simulation and computational cost. So in general, one can conclude that the boundary element cost is, parameter dependent. If you look at, for example, if you just increase the indentation depths, change the material properties, you will face a very soft material that requires a lot of, discretization in time and space, and it's very hard to solve. However, the Person and Bernard theory is also only available on the edge of this exploration space. So this motivates surrogate modeling that could be trained over the exploration space. So we just moved through a tabular classical machine learning model. We just considered all the normalized input parameter to the boundary element simulation and also the analytical simulation, and then we just give them as the input. And then we just try to predict the output, which is the pool of force. And in general, I mean, this could be a data-driven simple model, but we also considered the extended Person and Bernard theory that we developed previously in our previous paper. We just used it in coupled with that. It means that it also sees some parameters from the inputs and then predicts and provides another feature as the input to the machine learning model. And then finally, we will provide the predictions for the pool of force. We again plotted it. It means that y-axis is the pool of force. The x-axis is showing the unloading rate, and we just plot it. And then we have something like this. I mean, the analytical simulation is presented by the dashed lines. The training data is coming from the boundary element simulation. And the learning-based model that is predicted by the physics augmented machine learning model is shown by the dots. And the point is that, for example, for some simulation, through a relatively good computer, through numerical simulation, it takes for a single asperity or for a single, Hertz contact, you will need to spend 7 hours to obtain 1 point. However, through the, open source available online physics augmented that we presented, you can only spend 5 milliseconds to obtain that point. And then what is the point? I mean, we have a model that predicts exactly or relatively similar to the computational model, boundary element, and it also works closely to the analytical simulation. What is the point of using such a model? So we just, change the other parameters, the indentation depth, tabor parameter, and then you can see that changing these parameters, then the analytical simulation are not, able to provide well results. But the learning-based model that we provided is still providing similar results to the computational model. So in general, one can see that the model is working. And if someone is really interested, could just download the model from the link that is provided on the right side. I mean, all the codes and all the data are also available online, and the paper is also open source here. However, there is a limitation, which means that we are only predicting one scalar point, which is the pool of force. What we just described previously is that if someone wants to have the application in robotics and in manipulators, they need to control the forces, so they need to predict the whole time history. So is it possible to do such a great job? And so we just looked back at the data that we have, and we around more than 10,000 data, and we just looked at the data one. I mean, not all of them, but at least some of them. You can see 6 of them here. And then if you look at the distribution of the, for example, pool of time, it changes orders of magnitudes. And also, if you look at the forces, it's also changing orders of magnitudes. We have a sharp pool of instability in some samples. We have broad forces scales. We have history-dependent behavior because we are dealing with viscoelastic materials. And also, the most important thing is the variable event time. So if we just want to train a neural network simply on the data, so we have a bunch of data, and then we will put a neural network, then we will train it. Maybe, or actually, we need a very, very big neural network to be trained, different time scales, and then it be handle it. However, for such an application, it was not feasible. So we just came to the idea that if someone just applied the phase-wise discretization to the, model that we have, would be able to have a constant number of discretized points for each phase of the loading and also on the unloading or the unloading trajectory and the time history. So it means that instead of working on the constant delta t for the whole samples, we will have adaptive one according to the phase-wise discretization. So in that term, it means that we will have a sequence-to-sequence modeling of machine learning models. So we just did it. I mean, if you look at the figure, you will see that we just provided the time, displacement, and tabor to the model. Then the model will learn from the inputs, and the goal is to predict the output, which is the force. And the faded area means a bunch of data that we had, and we just tried to show 4 representative cases. As you can see, we're only using constant all the samples that we had. Then the other question is that, which type of neural network would be proper for training such data? So we just looked back again at the data and the physics that we have. The point is that the problem that we are solving is a viscoelastic material. So in fact, the force that we want to predict is not only depend on the current state, it also depends on the previous state. So it means that the force that we are dealing with is not only depending on the displacement that we are seeing in this step. So the current state is also a function of the previous states. And to include such history in the neural networks, it's really similar to the applications like translation and also the application like musical or video creation that they are using the stateful learning, the terms of stateful learning for. So if someone look at the stateful learning, some famous ones are the LSTM layers, long short-term memory layer, and also the convolutional layer. And they're completely distinct from something like feed-forward neural network and the dense layers. So we just, looked at the other applications, provide a lot of architectures. It's like changing the hyperparameters, and then come up with 6, unique architectures through those specific LSTM or convolutional layers. And then we just, did the training stuff like having 80% of the data for training, 10% for validation, and 10% for the test, and then we just plotted the validation loss through the mean squared error versus the epochs. Each epoch means an iteration learning, which means that seeing a whole bunch of data in each iteration, and then you can see the M1 predicts pretty well among all those. To select the models, we also look at the physics. It means the pull-off error, hysteresis error, and then finally the best one is that one. And the training time is not that much, and also because, as I described, because of discretization, the training time is not that much. And then we also looked at what if we just, instead of giving the displacement and time, giving some physical feature, and also physical insight to the model. It means that something like velocity, acceleration at each time of point, and also the edge properties. And the velocity could be also easily be computed through the finite difference. Acceleration could be obtained through the finite difference. And then the edge is computed through the change in the direction of loading and unloading. And then finally, the learning curve on the right side, you're seeing the validation loss versus epoch again. And through these simple changes in the features, you will see that even with the same architecture of M1 as I described, you will experience pretty much lower validation loss or error in the system. So the machine learning model could be predict or could also learn very fast and also very better. And finally, to understand that our model is going well, we just provided an input of loading protocol as I described to the model, and then try to see the effect of sweep on the Tabor parameter, which is the parameter for the geometry and material properties, and then see that if it is working proper or not. On the right, you are seeing the results of the prediction of the neural network, and the BEM solution is shown, or the reference that we want to predict is shown by the solid line, and the circles are showing the boundary element simulation. Sorry, the circles are showing the learning-based model results prediction. So you are seeing, even if we just zoom on the some part of the predicted area, and then look at the result of adhesion, despite these very sharp changes in the forces, one can obtain the adhesive force, which is very small. I mean, compared to the whole range of forces. And this is the final result that shows that the model is working properly in the region in between DMT-like behavior to JKR-like behavior. These are terms very famous in adhesive contact community. And then finally, we wanted also to see the final precision of the model. So we just plotted the histogram of pull-off force and also histogram of the distribution error of the hysteresis error. And then the quartiles are also based on the error that each sample has based on the mean squared error. And finally, one can see that our model, I mean, the quartiles is also, distributed among all the, distribution. But the good thing is that, for example, for the most test cases, one can expect lower than 6% of error for the pull-off, and also lower than 2% of error for the whole, hysteresis area error. So finally, we just conclude here, and then we developed a fast surrogate model for viscoelastic adhesion Hertzian contact. We also provided a physics augmented model in our previous work, we showed that the physics augmentation could also reduce the error by almost 60%. And finally, we just provided a sequence-to-sequence model, and validation against the boundary element simulation shows that accuracy trends from the JKR limit to DMT limit. And the future work would be transferring the experimental data into the system or extension of the model to more sophisticated problems. Thank you very much for your time and consideration.
Thank you very much. So you have essentially obtained a constitutive law for one asperity, one contact.
Yeah.
And what is your view on using this surrogate model to have multiple asperities?
Yeah, exactly.
And including pushing the limit where they start interacting, when they start to be very close to one another.
Yeah, thank you very much for your very good question. And actually, the last view that we had for the extension of this work was exactly what you mentioned. So it's like extending the current concept to a really more important problem, which is the rough contact problems, because in those problems, the computational cost and this discretization of the geometry and also among the time is much more important. So the next step is like that, and at least according to the results that we obtained and the inference time that each sample has, now, we foresee the possibility of the extension to that real-time adhesion prediction of rough contacts. Yeah.
So there are so many viscoelastic models in the literature. So
yeah.
Am I correct that your model is valid for one of them that you use for the training? And
yeah.
You have to redo all the training as soon as you change the model?
Actually, I mean, in our previous work that has been published in in International Journal of Solids and Structures, we use the modified power law. And if you look at the N here, it means that the power law material of viscoelasticity could be changed through changing that parameter inside our models. So, I mean, this could also, provide some possibility for that. Yeah.
Okay, thank you again.
Thank you.
Just